Hello everyone, welcome to Dakshana E classroom program. So in this chapter, the nucleus, up to now we have discussed about the nucleus. So what is exactly nucleus? We discussed about that. Then we talked about how nucleus is stable, why it's not like exploding because of electrostatic repulsive force between the protons. We also talked about actually that out of the available so many nucleus, why some are stable and some are unstable nucleus. We also discussed about the binding energy and binding energy per nucleons, that talk about how stable a nucleus is and on what factor it depends, and how we can calculate the binding energy and binding energy per nucleon, and how these things are related to mass defect by Einstein's energy, right? So we talked about that. In the last part also we discussed that those nucleus which are not stable means they are unstable. So why they are unstable, and when unstable nuclei basically decay, then in what way and what forms they decays. We talked about there are basically three type of decays, or three type of radiations are emitted from unstable nuclei, and with that the unstable nuclei break down or converted to new, is it, another nuclei, another atom, and how those things happen. So by this time we are in that position that we have understood about nucleus and unstable nucleus, and those unstable nucleus, they are how breaking down, we understood that. Now next point that we are going to talk about is basically the measurement of breaking down, means measurement of radioactivity. Means, let's say we have one sample of radioactive nuclei, okay? So now we are having sample, we are having, let's say, some n number of nuclei which are radioactive. So now if they are radioactive nuclei, definitely they will break down, is it? Now what I'm saying is that we have like n number of radioactive nuclei, so means there is possibility of decay of every nuclei, because like all n are radioactive nuclei, means all these nuclei are unstable nuclei, is it? And definitely every nuclei will be decaying, right? Now let me write, this is the instant when I am saying this is the t is equal to 0 time, right? At that time we have n number of nuclei. Now I will say, let's say at t is equal to, let's say, 1 hour, t is equal to, let's say, 2 hour, maybe t is equal to 3 hour, or t is equal to, let's say, 1 day. So if I just talk about any movement, is it, and I want to know how many nuclei will be there, can we say which nuclei will be broke down at what time? And like what we can say about these unstable nuclei disintegration. Disintegration means breakdown, is it? So that we are going to talk about now actually. So let me tell you few things about it, that is, you can write the fundamental law, is it, of radioactive decay. The point is, all these nuclei are unstable, definitely they will break down, is it? But still it's not possible to comment that at what time which nuclei will be decaying, right? We can't comment. The decay process which we study here, it's based on the probability of decaying actually, that we study in mathematics, is it? So, and that from phenomena, you know that actually radioactive decay, it's a nuclear process, is it? It's a nuclear phenomena, it is a nuclear phenomena, or the phenomena which happen in nucleus, is it? It happen inside nucleus. We already talked about that this radioactive decay, it's not affected by physical or chemical changes, is it? It's not affected by physical or chemical change. You can't control, you can't like change anything, right? It is purely, I mean, like the study of this radioactive decay we also call disintegration, is it? So the study of decay is purely based on the probability of decaying a or an unstable nuclei. Here, what I'm trying to say is that these are n number of nuclei I'm having at this time. Out of all these n number of nuclei, definitely I'm saying that, let's say if I'm considering infinite time, that every nuclei will be decaying, no doubt, understanding. But if I ask you, or if like we talk about that at any moment of time, is it, whether this nuclei will decay, this will decay, this will decay, it's not possible to comment that which nuclei will be decaying, right? It's not possible. We don't know when which nuclei will be decaying. So the probability, like decay process, it's an probability actually, that yes, we know, we have observed it, that there are different nuclei which decay at different rates that are naturally available. Some decay at faster rate, some decay at very slower rate. I mean, if we are having, let's suppose, some x gram of any radioactive sample, we have radioactive nuclei which basically reduces by half in some milliseconds, some seconds, or like very small interval of time. Or we have some radioactive nuclei also which reduces by half in some million and billion of years also, understanding. Means if this is the zero time at which the number of radioactive nuclei available is n, then we have few radioactive nuclei or sample which, like, where I will say the number, these are radioactive nuclei, so the number of radioactive nuclei will become half. This time some we have like milliseconds or few seconds. I mean, like, we have some radioactive nuclei which reduces by this half in this much interval of time or this much duration, and also t is equal to some million and billion of year. Means some take only few seconds and even less than that, and some take even million and billion of years to reduce or to decay half of the radioactive available nuclei, understanding. So now we just want to see, like, here the point is that it's definitely already clear that it's not in our control. We can't control, we can't say that okay, this, let's increase the temperature and let's decrease the pressure and like anything like that, apply electric field, magnetic field, and by that we can be controlling their activity. Now it's becoming faster, now radioactive like rate is slow. No, we can't do that actually. It's not possible, it's not in our hand, understanding. So whatever it's like, it's happening naturally, is it? They are decaying. Yes, we have some like artificial radioactive processes also, where we bombard, we make it to unstable, and then we decay that is there, but right now I am talking about the natural radioactivity. So I am saying is that we can't control. It's like all the radioactive sample which are available in the nature. We have gone through all of them and we have studied that how they are decaying. So some decay at faster rate, some decay at slower rate. Now we just trying to understand that how we can express all those things mathematically, how we can relate by using the data which has been available or which is available to us by the scientists who did a lot of research and studies on their like activity and all that understanding. So we are just trying to understand that how things are working here actually. Okay, so these are few points that it's like completely probability based basically. Here we do not talk about the surety. We can't definitely say at any time which nuclei will be decaying, is it? It's not possible to comment that at any time which nuclei will decay and which will not. That's not possible. So it's just probability based. We try to understand the probability that okay, there is high probability, there is low probability, there is probability. So that we only understand, like talk here, we study here. So these are few things. So now what we are going to see is that let's say at any time we have like first thing is like how we can define. So there are few terms basically, that is activity, is it? So measurement of radioactivity basically. Activity or decay, is it? So here actually we measure it into, I mean like let's say let at t equal to 0 and not number of radioactive nuclei are present in any sample. Okay, so this is all like observed experimental things, that this is how these are things happen, this is what observed. So it's like that. So I'm saying like at t is equal to 0 and naught is the number of radioactive nuclei present, right? After some time, let at time some t, is it, number of radioactive nuclei present is let's say n. So means out of n not available, some has decayed by this time. Clear? Now at t time, number of available, so definitely I will say n will be definitely less than n naught, means number of still available radioactive nuclei will be less because some has been decayed. Okay, here decay means you must be understanding what I mean for decay. Decay means its nuclei is converting to different nuclei, is it? Like uranium, so it was like I told you in the last lecture, uranium 235, 236, 237, 238, they decay and finally converted into like lead or sometimes bismuth also, is it? So that is like it's converting, I'm like finally nucleus or atom is changing to another form. So this we define as decay, is it? So decay, I will say, means conversion of one radioactive nuclei to another, may be stable or radioactive nuclei. That conversion we call decay, right? Okay, so now here this is the thing at T time, right? Next thing is, so means like at this point of time the probability that how many nuclei will be breaking down, at this time the probability that how many nuclei will be breaking down, it's all experimental observations we studied, and from these results we are writing it actually, is it? So decay you understood, is it? Now so the probability of decay, is it? Decay we also write it, we measure it into disintegration per second, that is the SI unit of radioactive decay. I will write that. Okay, so the probability of decay, is it, is directly proportional to number of radioactive nuclei present at that time. These are all experimental observations. If we are having, let's say, one sample and we have, let's say, 1000 radioactive nuclei, then in 1 second if I talk about that probability of decaying, that how many nuclei will be, so let's say it's X, is it? Now if I increase the number of radioactive nuclei in the sample, let's say to 2000, is it? Now the probability of decaying like number of nuclei in same time, then it probability will increase double, because now radioactive nuclei has double, so there are more chances of breaking down of more number of nuclei, and this also satisfy the practical or experimental observations, right? So here we can write, and this decay we measure into like dN by dt, we also call it activity. Okay, so see here about we are talking about measurement of radioactivity. So I just write it, let's say sample we have, and N naught is the number of radioactive nuclei present at T is equal to 0 time, right? So 0 time, it's N naught number of radioactive nuclei. Let's say at T time, N is the number of radioactive nuclei. So means out of N naught, some N naught minus N has decayed, means converted to another nuclei. Let at time T equal to T plus dt, the number of radioactive nuclei left is N minus Dn, because this at T time it's N, so in dt time I will say in time dt number of radioactive nuclei decayed, that can be written as dn. So I can, this means, just try to understand it, means I can say in this interval of time these many number of nuclei has been decayed, is it? So I can write one another term, that how many decay are taking place per unit time, is it? So number of decay per unit time, right? That I can write, it's dn by dt, is it? Number of decay, and this quantity we call basically activity, and this radioactivity is measured in terms of activity. So or I will say better, the radioactivity radioactivity or radioactive decay is measured in terms of activity, and activity, it is number of decay, or decay is also called disintegration, per unit time. Is it? First thing is radioactivity is measured in terms of activity. And what is activity? Activity means it is the number of decay or disintegration per unit time. So we define activity AC, this is equal to dN divided by dt. Clear? So this is the, in SI unit we write it disintegration per second. Disintegration per second, we also call it dps, and 1 dps is called 1 becquerel because Henry Becquerel discovered the radioactivity. So in their honor we write the SI unit of activity is called 1 becquerel. This is also BQ, denoted it by terms BQ. So 1 BQ means 1 becquerel. This is the SI unit of activity. Let me erase this part. Okay, and here disintegration or activity is also measured in dpm, dph, dpd, so on. Means disintegration per minute. This is disintegration per hour, per day, and so on, right? SI unit is disintegration per second. One disintegration per second is also called 1 becquerel. Is it? This is also called denoted by BQ, also the SI unit. Activity means you should clear, you should understand, means radioactive nuclei are decaying. So in 1 second, in 1 unit of time, how many nuclei will be probably decaying, or there is for how much probability is there that in 1 unit time how many nuclei will be decaying. We measure that, we call that activity of radioactive nuclei. SI unit, this measurement can be in terms of these terms, and you must be knowing that Pierre Curie and Madame Curie, is it, both discovered radium and polonium, two radioactive nuclei. In their honor actually, or they found that actually 1 gram of radium has activity of 3.7 into 10 to the power 10 dps, and this is also termed as 1 Curie. 1 Curie is also 1 unit of activity, disintegration per second, basically not this, and this is equal to 3.7 into 10 to the power 10 disintegration per second. This is simply termed as 1 Curie, right? So 1 Curie means 3.7 into 10 to the power 10 disintegration per second, or you can say also Becquerel. Is it? Similarly, Rutherford also there is another unit 1 RU, and that is equal to 10 to the power 6 dps or 10 to the power 6 Becquerel. So these are some other unit for the measurement of activity. So by this time simply you should be understanding what is the meaning of activity. Activity means one unstable or radioactive nuclei is decaying, right? Then per second or per unit time how many nuclei will be decaying, right? Simply that we call activity. Clear? Okay, so let me just erase it. Okay, so activity should be clear with everyone. Activity means rate of decay, also denoted by sometime R, sometime A, and this is equal to dN by dt. Is it? Now, the experimental study suggests that the activity of any sample, radioactive sample, is directly proportional to number of radioactive nuclei, right? So I will say this dN by dt equal to activity is directly proportional to n. N is the number of radioactive nuclei present at t time. Understanding? Right? So now, and here we write this implies activity equal to dN by dt is this proportionality is removed by lambda and n, and we write here minus sign also. Now this lambda, this is called decay constant. And lambda for a particular nuclei it's constant. Lambda you will write depends only on the radioactive nuclei. Means if I say I talk about one radioactive nuclei, let's say uranium 238, then for that lambda will be constant. Is it? If like you are changing the nuclei, then only your lambda will be changing, lambda will be different. For one particular nuclei, it doesn't matter at like how many radioactive nuclei are present at any time. Is it? Whether it's like large number of radioactive nuclei, small number of radioactive nuclei, high temperature, low temperature, nothing. So simply lambda depends only on the radioactive nuclei, remaining things like it's constant. Is it? So lambda does not depends on anything else. It depends only on radioactive nuclei. So one particular radioactive nuclei, it's constant. Clear? Another thing, this what exactly it tells. So lambda is tells about the activity of nuclei, or I will say if activity is higher, what it means the decaying process is faster, means it's will decay even at higher rate. Is it? So I will rate A is directly proportional to, like A is proportional to lambda, means if lambda is high implies activity is high, means decay rate is faster and also implies the radioactive nuclei is less stable. When it is decaying faster means it is less stable, then only it is decaying faster, right? If it is decaying slower means its stability is higher, is it? So you can write this implies smaller the value of lambda, more stable is the nuclei, right? So this is about lambda, it's called decay constant. It's not depending on any factor excluding the nuclei itself. When you are changing the nuclei, then lambda will change. Otherwise, even if like number of radioactive nuclei are higher or smaller, it doesn't matter. Lambda for one particular radioactive nuclei is constant, is it? So one particular radioactive nuclei, it does not change. Lambda tells you about the activity, it tells you about the stability of nuclei. If lambda is higher means the nuclei is decaying faster. When it will be decaying faster? When it is less stable. So similarly, I can say if lambda is smaller for one particular nuclei, is it? Then I will say smaller means its decay constant is smaller, means activity is smaller, means that nuclei is more stable, right? So I will say, if let's say I have two nuclei A and B, let A and B are two radioactive nuclei. I will say lambda 1 and lambda 2 are their decay constant, and if lambda 1 is greater than lambda 2, this implies A is more, or you can write unstable. I will write better right in terms of stability, so I will write B is more stable than A, is it? Or you can write A is more unstable than B. That is the meaning of lambda, is it? Okay, so now we know that actually at t is equal to 0, number of radioactive nuclei and not at t times. So then can we have some relation that at any time how many nuclei will be present, radioactive nuclei, how many will be decayed, like all those, how many B particle will be formed, like that. So yes, we can find those also. That is also very easily. So let me just erase it. Let me do it. Okay, so let's consider we have one radioactive nuclei A which is decaying to like another nuclei, or I will say stable nuclei B, is it? The decay constant for this process is lambda, and I will say at t is equal to 0, number of N naught is the number of radioactive or number of nuclei present. So t is equal to 0, A has N naught number of nuclei, B has 0, means there is no B particle present at t is equal to 0. I will say at some t is equal to t time, it is N, and how many like B will be there? So if let's say N naught was earlier, N is present now, means how many have been decayed? N naught minus N, and exactly those many nuclei of B will be formed. So I can write this is N naught minus N, is it? So number of nuclei present at this time. So what we know is that from activity I can write A is equal to dN by dt is directly proportional to N, and this implies dN by dt is equal to minus of lambda times N. Yes, there is one more thing I need to explain to you. So here this, what is this minus sign? Here, see, this is what is this? This is the activity. Now, if I say at t is equal to 0 time, 100 nuclei are present, so activity will be faster, right? After some time, let's say 5 seconds, 50 nuclei are present, then now I can say definitely the number of radioactive nuclei is smaller. So activity means the decay rate will be also smaller. So actually this quantity rate means I will write rate or activity decay with time, but here n and lambda both are positive, there is nothing. So to balance the sign both side we write here minus. Is it because this quantity activity is decreasing, so it will be like negative, right? That's why to balance this negative sign is showing negative sign implies the activity is decreasing with time, or number of radioactive nuclei is also decreasing. So that is because at any time if I say n is the number, it's just simple number, so it's some positive, lambda is constant, and this is negative means like to negative then positive, that doesn't make sense. Is it how these two quantities can be equal? So to make them equal we multiplied here with one more negative sign. Okay, next thing is we can write, now we want to find the number of active radioactive nuclei present at any time, number of nuclei decayed at any time, like that. So we got this relation here, you understand the meaning of every term. Next thing is very simple, let me integrate it, rearrange it. So I can write dn is equal to minus lambda n into dt, and let me send it this side. This implies dn by n equal to minus of lambda into dt. Let's integrate it both side. Is it? Now we need limit, so t is equal to 0 time, and what is the n limit? So we know 0 time n is equal to n naught, t time this is equal to what? N. Integrating both sides, what I'm getting, it's ln n divided by n naught, directly I'm substituting the limit also, equal to minus lambda, this is t. Let me substitute here 0 to t. So then I can write ln n by n naught equal to minus lambda t. This implies n is equal to n naught e raised to power lambda t. So what is this n? N naught, number of radioactive nuclei present at t is equal to 0 time. Lambda, decay constant, t at any time t. So at time t, n is showing you the number of radioactive nuclei left. Is it in the sample? N is the number of radioactive nuclei left at time t. Is it? Now next thing is, you can see easily, this is simply what? Exponential function. I can plot it actually, and that should be even like make sense to you, that definitely the number of radioactive nuclei will be what? It's decreasing and decreasing exponentially. So we can plot it, plot the graphs. It comes like this actually. So this is at t time, this is n number of nuclei, this is n naught. So at t is equal to 0, number of radioactive nuclei present is n naught, and there it is decreasing exponentially. So this is the graph of number of radioactive nuclei present at any time. Is it? So that number of radioactive nuclei, n is number of radioactive nuclei present versus time, graph is this, right? Similarly here, let me just erase this part only. So now you understand, n is what? Number of nuclei of A, radioactive nuclei present at time t. Is it? So number of nuclei of A decayed by time t, I can say as many as number of A nuclei decay exactly that many number of B nuclei will be formed, is it? So I can write this is also equal to number of B nuclei formed, and that I can write it's equal to what? N naught minus N, because t is equal to 0 time, this is the number of A present. At t time, this is the number of A left. So this minus this is decayed. This minus this is the number of nuclei A has decayed, and exactly that many number of nuclei of B has been formed. So I can write it here, it's N naught minus N can be substituted, N naught e raised to power minus lambda t. This I can write N B also, or N A decayed, and this is equal to N naught 1 minus e raised to power minus lambda t. I can plot this graph also. So this you will write either NB or NA decayed versus T. So you can write at T is equal to 0, what will be the, like this, T is equal to 0, you can substitute it here, it's 0, and then it's growing exponentially. So this like this, is it? Finally it will be like N naught at infinite time. Is it? So this is the variation of, so I think it's very easy, straightforward, simple thing. Now we are counting, we understood the reason why this that all happening, what is the meaning of decay. We are going mathematically on that, how many nuclei present at time, how many decayed, like that. So how we do the measurement? This mathematics is simple exponential function, basic calculation part. This is the like basically measurement of radioactivity. So measure in radioactivity in terms of activity, and activity is what? Rate of decay, means per second how many radioactive nuclei are converting, are decaying to stable or another unstable nuclei, depending on, right? So this is basically, so here we define this like number of radioactive nuclei of A left, number of radioactive nuclei of A decayed, or that is also equal to B formed, their variation, mathematical expression. So if anything is asked to you, you should be able to answer that, right? Okay, so now by this time we can express the number of nuclei of A or B present at any time. T is equal to 0, A converting to B lambda, this is N naught, this is 0, and T time, this is N, and this is N naught minus N, is it? So I got actually N equal to what? N equal to N naught e raised to power minus lambda T. This, right? Now we already defined activity, so let me just write activity is equal to what? dN by dt. This means I can differentiate it, then also I will get activity. So this is differentiating this d by dt of N naught e raised to power minus lambda t, and this implies it's coming out to be lambda naught e raised to power minus lambda t. Minus sign is also there, is it? Right. Okay, just one second, this is N equal to this. Okay, so this is minus N naught into lambda divided by this is okay, and we can write actually this quantity is what? Initial activity. So we can write d activity is equal to dN by dt. This can be written as A naught e raised to power minus lambda t. A naught means activity at t is equal to 0 time, because you can write here actually activity is what? dN by dt, this is equal to minus of lambda, and if I substitute it here also, then it's N naught e raised to a minus lambda t, You can get it from there also, it's same thing actually, right? Now here if I substitute at t is equal to 0, then activity is what? dn by dt, and this is equal to what? Minus of lambda n naught e power minus 0, and that will be minus lambda n naught, and this I am defining exactly activity at t is equal to 0 at same thing. So we can express activity also in this way. Just remember this simple things are there. So activity is equal to dn by dt, and this you can write also minus lambda n naught e raised to power minus lambda t, also equal to a naught e raised to power minus lambda t, and this is the relation in terms of n naught. So now we can get the activity at time t, we can get the number of active nuclei, number of decayed nuclei, and so on. Is it? So there comes something like that. Okay, at what time is it? If I say this is the 0 time started, things started, then at what time the number of nuclei of A left will be half, or I can say at what time the number of nuclei of A decayed is also half, right? So we define one more term that we call half-life. You should remember this, also important thing. It is the duration of time by which the number of by which half of the radioactive nuclei has decayed. It is that time. Half-life means it is the time by which, if I say, see, simple thing, 0 time number of nuclei, active nuclei is n naught. At t time the number of nuclei is n. So I am writing it what time, what is this time at which the number of nuclei left is half, means at what time n will become n naught by 2. Understanding? That time duration we define as half-life. Is it? So I can write this means at t equal to t half, I can write n will be n naught by 2. Is it? It's that time where number of nuclei left or decayed both will be like half of initial nuclei. So that we can already write n is equal to n naught e raised to power minus lambda t, and this should be equal to what? N naught by 2. Clear? Let's simplify it, and I am taking ln both sides, so it's ln e raised to power minus lambda t. This is equal to ln 1 by 2, and you can write it's basically minus lambda t minus ln 2 gets cancelled, and t half is equal to ln 2 divided by lambda. This is called half-life. You should remember it, it's important. We substitute the values of ln 2, then it comes 0.603 divided by just wait, ln 2 is equal to 2.303. just let me just, so it's 2.303 L log 2 divided by lambda, and log 2 is 0.301. Is it? So it comes basically let me just 1 second. So just simply simplifying it, multiplying it, it's basically 2.303 into 0.301 divided by lambda, and simply multiplying it, it comes 0.693 divided by lambda, or you can write ln 2 divided by lambda, both mean same. This is the half-life. So you must understand the meaning of half-life. Half-life means it is the duration by which the number of radioactive nuclei left will be also half of initial value, or you can say number of decayed nuclei will be also half of initial value. Is it? and like initially it was 0, then decayed nuclei will be half, right? So like that actually. So this duration we defined as activity, sorry, half life. Okay, so you must be clear here now with half-life. Half-life simple means by it is the duration, the time by which half of the nuclei has been decayed. Is it? So we got that expression T half, we write it T half equal to 0.693 divided by lambda or ln2 divided by lambda. That is your T half, right? So I will say number of nuclei left after n half-life. One half-life, I can say it's half of initial, that is n naught by 2. Then how many like radioactive nuclei will be left after n half-life? So this I know the relation n equal to what? N naught e raised to power minus lambda t. Now t is equal to what? N t half. That means n ln 2 divided by lambda. Let me substitute simply it here. So n is equal to n naught e raised to power minus lambda into t is n ln 2 divided by lambda. Clear? Lambda gets cancelled. N equal to n naught e raised to a minus n ln 2. Is it? I can simplify it further. So n equal to n naught e raised to power, I can just simply like make it ln 2 power minus n. Is it? And this is e power, this is coming out to be e naught minus, this is simply multiplied by 2 power minus n, and this implies n is equal to n naught 2 power n. So means the number of radioactive nuclei left after n half-life is n naught divided by 2 power n. So means after one half-life n equal to 1, number of nuclei is n naught by 2. After 2 half-life, number of active nuclei, radioactive nuclei is n naught by 4, and after n half-life I can write this. Similarly, we can write exactly activity also, is it? So activity, you can say, see, activity also actually reduces by half exactly, because activity is proportional to what? Lambda is constant, activity is proportional to n, and exactly after half-life n also becoming half means activity will be also half, is it? And you can even see it from here also. A is equal to dn by dt equal to a naught e raised to power minus lambda t. You can write it, even check it from here, a naught by 2, that exactly at what time it will become half also. So by this way also, it's my taking ln directly I'm writing, so it's ln e raised to a minus lambda t, this is equal to ln 1 by 2, and this implies minus lambda t equal to ln 2 minus, and t is equal to t half equal to exactly we are getting same thing, is it? So you can say, but in exactly same t half time, activity also become half, right? So I can also ask, or I can also calculate exactly the activity after n half-life, is it? Activity after n half lives, is it? This will be like, I can write a is equal to dn by dt equal to a naught e raised to power minus lambda t. Again I can substitute t is equal to what? N half-life means t is equal to what? N lambda, n ln 2 by lambda. So let me substitute it here, a naught e raised to power minus lambda n ln 2 divided by lambda. Clear? Lambda gets cancelled, activity is equal to a naught e raised to power minus, this is n ln 2 This implies minus, I can send it inside, so it's a naught e raised to power ln 2 power minus n. This is a naught e raised to power minus 2 power minus n, and this implies a is equal to a naught by 2 power n. So we can see here exactly the activity and number of nuclei varies exactly in same manner. Why I am deriving these relations? Because in problems you will be asked that how many, like what will be the activity after n half-life, what will be the number of active nuclei left after n half-life, what will be the number of decayed nuclei after n half-life. Similar such type of problems are asked. So by this time you should be clear with that. I think like simple relations are simple, things are very easy, straightforward. What is exactly happening, you should be feeling it here exactly, that we have active or radioactive nuclei, they are decaying, how we are measuring that, on what things they are depending, all those things should make sense to you. So these are few relations you should remember, these are important, we will solve some problem based on them. Okay, see one simple application. So a radioactive sample has n naught equal to 6.0 into 10 to the power 18 radioactive nuclei at some certain instant of time. Let me write it 0 time. How many of these nuclei will still be in the same active state after 2 half-life? If we just try to understand, it means it's simply asking the number of active or radioactive nuclei left after 2 half-life. One way is we can directly go with the formula. Is it straightforward? So we can number of radioactive nuclei left after 2 half lives. So we know that formula, that is n naught divided by 2 power n. So it's talking about 2 half life, that means n naught divided by 2 power 2, and this comes out to be n naught power 4, n naught by 4, and this is 6.0 into 10 to the power 18 divided by 4. You can get it exactly. So it's right, 1.5 into 10 to the power 18 nuclei. Is it? You can understand it in another way also. Half-life means number of radioactive nuclei become half. Is it? So we can understand it in different way. After 1 half-life, number of radioactive nuclei left, what you can write, this is equal to what, n naught by 2, and after another half-life, half of these after second half-life, I can write it's n naught by 2 into half of that, and that exactly comes out to be same thing. So simple straightforward problem is that. So we can see the application of this formula just we saw. Okay, so this is all about today's lecture. Let's continue from here onward in the next class. Thank you so much.